Welcome to the standardization of NaOH and buffers. Standardization is the process of determining the exact concentration or molarity of a solution. This is often done by titration, using a primary standard like KHP, freshly boiled water, and the proper indicator. A buffer is a solution that resists a change in pH when acid or base is added. This is made by mixing a weak acid with its conjugate base, or vice versa. It is important to use a standardized solution when preparing a buffer, so the quantities of solution added can be precisely and accurately known. First, we will be learning about the standardization of sodium hydroxide. Reagent-grade sodium hydroxide must be standardized using a primary standard because it contains absorbed water and carbonate from its surroundings. A primary standard is a reagent that is pure enough to be used directly for comparative measurements after weighing. Primary standards display unique characteristics that make them ideal for making accurate and dependable assessments of concentration without the need for specialized equipment. These characteristics include high purity, low reactivity with the air or surrounding environment, low hydrocophicity or ability to absorb or release water, large molar mass, and a predictable reactivity. Pure KHP is used as the primary standard for the standardization of sodium hydroxide solutions. It is a weak organic acid with one ionizable proton, so it acts as a monoprotic acid. This means that the KHP and NaOH react in a 1:1 mole ratio in this titration. KHP is a stable solid that is easily and accurately measured by mass, which is important in any primary standard. The structure of KHP is shown on the right of this slide. It is important to use freshly boiled water and dispense the sodium hydroxide solution without excess exposure to air, so the concentration is not changed by substances in the air or absorbed by the water. Freshly boiled water ensures that all the dissolved carbon dioxide is removed. It is important that carbon dioxide is not present to interfere with the NaOH because it is capable of absorbing large amounts of carbon dioxide from the atmosphere. If this occurred, it would change the determined concentration of the sodium hydroxide. An indicator is any substance in solution that undergoes a distinct visible change, like changing color, as it reacts with either an acid or a base. Choosing the appropriate indicator is essential because each indicator changes its color over a particular range of pH values. Indicators are selected by the pH that you would like to see a color change, and for this experiment, it is expected to see a color change in the solution when the pH is about 9. Indicators for acid-base reactions are either weak acids or weak bases. Phenolphthalein is a weak acid that changes between a clear and pink color between the pH of 8 to 10. In aqueous solution, the phenolphthalein dissociates slightly, forming an equilibrium, where the weak acid phenolphthalein and water appear clear on the reactant side, while the product side, including hydronium ions, appears pink. This makes it evident to see which side the phenolphthalein equilibrium is favoring by the color that it appears. Le Chatelier's principle states that when an equilibrium is disturbed by applying stress, the equilibrium will shift to relieve the stress. The excess amount of hydronium ions in an acidic solution will cause a shift to the left and favor the formation of the phenolphthalein, so a clear solution is observed. However, when there is an excess of hydroxide ions, they react with the hydronium ions to form water. This shifts the equilibrium to the right because water is being formed and hydronium ions are being removed, so a pink color is seen. The change in color is used as an indication that the endpoint of the titration has been reached. To calculate the exact molarity of the sodium hydroxide, first calculate the number of moles of KHP in each flask using the weight of KHP in the flask and the molecular weight of KHP. Then calculate the total volume of sodium hydroxide used to titrate each KHP flask to its endpoint and convert the milliliters to liters. Because KHP and sodium hydroxide react in a 1:1 mole ratio, the number of moles of KHP can be used as the number of moles of NaOH. Divide the number of moles by liters to find the molarity of the sodium hydroxide. Report the standardized sodium hydroxide concentration as the average of 3 trials that are within 1% relative standard deviation of each other. Now, pause the podcast, read this sample problem, and see if you can do it on your own. For this problem, you simply convert the grams of KHP used to moles of KHP by using KHP's molar mass. Then, you convert the milliliters of sodium hydroxide used in the titration to liters. The moles of KHP used can be used as the moles of sodium hydroxide because they react in a 1-to-1 ratio in this titration. Then you put moles and divide it by liters to find the molarity of the sodium hydroxide. It is necessary to know the precisely and accurately found concentration when preparing buffers. Now that you know the specifics on how to standardize NaOH to find this precise and accurate concentration, we will learn a little bit about buffers. As mentioned before, a buffer is made up of a weak acid and its conjugate base, or a weak base and its conjugate acid. For example, acetic acid and its conjugate base would make a buffered solution because it is a weak acid, but hydrochloric acid and its conjugate base would not because hydrochloric acid is a strong acid. If an acid is added to the buffer, the conjugate base reacts with the hydronium ions to neutralize them. This maintains a constant pH in the solution. If a base is added to the buffer, the weak acid neutralizes the hydroxide ions to maintain a constant pH. Now for some of the properties of buffers. If a buffer is diluted, it maintains the same pH as the non-diluted buffer. However, each buffer has a capacity, which refers to a measure of the efficiency of a buffer in resisting changes in pH. A diluted buffer has a lower capacity than the non-diluted buffer. The more weak acid and conjugate base a buffer contains, the higher the buffer's capacity. Now, pause the podcast, read this sample problem, and see if you can complete it on your own. The answer will be given on the next slide. This problem refers to the properties of buffers. The new diluted buffer would have the same pH as the original buffer because when a buffer is diluted, the pH does not change. The new diluted buffer would, however, have a lower capacity than the original buffer because when you dilute a buffer, the capacity decreases. The pH and Ka of buffers are directly related. The Henderson-Hasselbalch equation shows the relationship of the two in a buffer. It states that the pH of a buffer is equal to the pKa plus the log of the concentration of the base over the concentration of the acid. The log of 1 is 0, so if there are equal moles of the acid and its conjugate base in the buffer, pH is equal to pKa. pH is the negative log of the hydronium ion concentration, so pKa can be found by finding the negative log of the Ka value of the acid. A buffer works best when the ratio of acid and base is as close to 1 as possible. Now, pause the podcast once again and read this sample problem. Attempt to complete it on your own and then check your answer on the next slide. First, you find the pKa by taking the negative log of the given Ka. Then you plug the pKa and pH into the Henderson-Hasselbalch equation. Solve this equation as shown to get the ratio of base to acid. You should find that for every milliliter of acid, 12.30 milliliters of base should be added to the solution to prepare this buffer. Here we have a titration curve, which is a plot of the pH versus the volume of titrate added. The titration curve shown on the right marks the equivalence point and the half equivalence point of the titration. The equivalence point occurs when the moles of base added equals the moles of acid. The half equivalence point occurs when the moles of base added is half of the number of moles of original acid. So the number of moles of acid equals the number of moles of base. Therefore, the half equivalence point is the point in the titration where the solution acts as a buffer, because the number of moles of acid is equal to the number of moles of base. Therefore, the ratio of acid to base is 1, so the pH is equal to the pKa at the half equivalence point of a titration. Here we have another sample problem. Pause the podcast and complete it on your own. So, for this problem, you can see on the titration curve that the pH is 4.5 at the half equivalence point. At the half equivalence point, pH is equal to pKa, so the pKa is 4.5. You can then find the Ka because pKa is the negative log of Ka. So you would do 10 to the negative 4.5 to find the Ka of this acid. Buffers are present in many ways in our everyday lives. Carbonic acid and hydrogen carbonate keep the pH of blood at 7.4. Without this buffer, drinking a soda would make your blood pH so acidic that you would die. The same buffer in blood is also in swimming pools, keeping the pH between 7.2 and 7.6, so the water does not irritate people's skin. Lastly, citric acid and sodium hydroxide in shampoo balance out the natural alkalinity of soap. Otherwise, the shampoo could easily burn your scalp. Lastly, we have some problems to check your understanding of the topics introduced in this video. If you are having trouble, look back to the information on the slides and the sample problems in this video. First, it asks what would be the best indicator to use for a titration that expected a color change around the pH of 7. Use the following chart that shows the indicators and the pH ranges in which their color changes. Then select the best answer given. The next multiple choice question asks you to find the pH of an acid at its half equivalence point if the Ka of this acid is 5.6 times 10 to the negative fifth. Round your answer to 1 decimal place. Now there are some free response questions. This one says a student was standardizing sodium hydroxide with the primary standard KHP. If the final reading on the burette was 49.60 and the initial reading was 4.75, and the student found the concentration of the sodium hydroxide to be 0.2137, how many grams of KHP did the student initially use? Lastly, we have a question that asks what is the pH of a buffer that consists of a 0.25 molar NH4Cl solution and a 0.10 molar NH3 solution if ammonia has a Ka value of 5.6 times 10 to the negative 10. Complete these 4 problems on loose leaf. Thanks for watching!